Hello everyone. So I got asked a few questions about solving a problem that involves heat removal, heat exchanger, and a multi-reaction problem. So we're going to go through that one right now. One of your classmates was able to find this problem and asked me to solve it, and so let's dive right into it. So we have this complex gas reaction. You have 2A going back and forth between 2B. It's giving you the reaction rate, and one thing to note right here is that it's giving you RA. So this reaction rate is in terms or respect to the component A. You have the delta H of the reaction, the heat release reaction. Notice that this is also in terms of moles of A. So you would have to, at some point, you know that these two are going to match up. Next, we have the second reaction, 2B, combining with A to give you C. This is giving it to you in terms of C. So this reaction rate law is in terms of C. And also this heat of formation of the reaction is in terms of moles of B. So right off the bat, I know that these two don't match. So going forward at some point, I'm going to have to keep that in consideration. So we're given that this complex gas phase reaction is carried out in a PFR with a heat exchanger. Pure A is entering at a rate of 5 moles per minute at a concentration of 0.2 moles per dm cubed at a temperature of 300 K. The entering temperature of an available coolant is 320 K. Then it gives you some available information. Take note here that each one of these K values is given at different temperatures at 305 K, 310 K, and 315 K. So we're going to have to know right off the bat, I'm thinking that we're going to have to apply the Arrhenius equation for all these different Ks. Next, it says that the equilibrium constant is with respect to A in reaction 1 when using the Van 't Hoff's equation, which is S12-4. And then it gives us a list of constants. So it's giving us our U of A, our specific heat capacity for our coolant, our specific heat capacity for all of our different reactants, and then also our R value and our mass flow rate. It's going to be the mass flow rate of the coolant, M dot C. So the first thing it's asking, and then of course it's giving you the volume of the reactor is V. Then it's saying plot all of the flow rates. So right here, it's saying plot flow rates. So I'm going to assume that I'm going to be doing dF terms. So we want d flow rate of A, d flow rate B. We're not going to want to use conversion because it doesn't ask us for conversion at all within this problem. So we don't have to worry about conversion. And then it also says the plot temperature inside the reactor versus the ambient temperature, TA, on a separate graph. Versus heat with a adiabatic operation, heat exchanger with constant temperature A, and then co-current and countercurrent. So let's just dive right into this then. So first, we're going to start with the picture. We have a plug flow reactor. We have pure A entering, and this is just pure A. And we have that the flow rate of A initial is 5 moles per minute. And we have our concentration of A initially is equal to 0.2. Our temperature initial, our inlet temperature is 300. And then somewhere, for a cooling jacket, we have a, some temperature ambient available is 320 K. It's our inlet. So it'd be, I guess, TA naught. And then the first thing that we're going to want to do is, let's just start with a mole balance. So we know that we want our flow rates of A, flow rates of B, and flow rate of C versus volume. And then we also want a separate graph. So we want T and TA versus volume as well. So we need to figure out equations that gives us flow rates as functions of volume and also temperatures as functions of volumes. So what we want is we want all these different species as a function of volume, and then we want temperature as a function of volume as well. So first thing we're going to want to look at is, if you look into lecture 6, so we look at lecture 6, slide 12, it tells you that for flow systems, if you're looking at for flow rates, you have just these equations right here. Okay, so this is just all just to say that you have your flow rate of A, your change in flow rate of A, and your change in flow rate of B and C are just equal to your rate of reaction of each component, which makes sense because there shouldn't be a change, or at least the only change in flow rate would have to be as a result of things being reacted. We don't have any inlet, we don't have any outlet. Well, we have an outlet, but we don't have anything diffusing out to the sides. So our flow rate change is only going to result as the rate of reaction of each specific species. So that's great. We have a starting equation that doesn't look too bad. Now we have to figure out what are all of these R's, RA, RB, and RC. So to do that, let's look at our RA. Our rate of reaction of A is equal to, well, we just got to look at this reaction over here. When we have different reactions, we have 2A going back and forth between 2B. Looking over here. So we have to do stoichiometry. So let's rewrite the equations, the reactions over here so we can see what's going on. So right here, we have reaction 1 and reaction 2. And we know that from stoichiometry, if we're looking at just reaction 1, we know that the reaction rate of A over 2 is going to be equal to our opposite of the reaction rate of B over 2, which is all just to say that the reaction, we should say 1, and we should say 1. Reaction rate A1 is equal to the opposite of reaction rate B1. Easy enough. Reaction rate 2, we've got 3 components now, so we know that the reaction of B2 over 2 is equal to the reaction of A2, which is equal to the opposite of the reaction of C. And we can call it C2, but there's only one C. So we know then that our reaction of B2 is equal to twice that of the reaction of A2, excuse me, and minus twice that reaction C2. Okay, so for reaction rate of A is going to be equal to, if we look back over here, it's equal to RA1 plus RA2, which is equal to, we have to look at what is the terms given in our reaction rate. So this is given in terms of A, so we can just leave it alone for the first reaction rate. So we would say, well, that is just equal to, and you can say negative, here's where you have to keep track of the negatives, right? So for this one, I'm going to redistribute the negative back over here. It doesn't matter, just as long as you don't add an extra negative. So this is going to be equal to, okay, so that is the first contribution for our RA1 right there. There's a little bit, it's starting to get a little messy, so I'm just going to move some stuff around really quick. Okay, now we have enough room. So we took care of our RA1. Now we have to figure out what is our RA2. We know right here, if we look back at the problem statement, that for the second reaction, it's giving it in terms of C. So we have to say this reaction is in terms of C. So we have to look at our stoichiometry here and say, okay, well, reaction rate A, if we just look at this portion right here, reaction of A for reaction 2 is equal to the opposite of the reaction C2. So it's just all it is you're just using this equation and sticking a negative in front of it. So let's plug that in. Okay, so that is our rate of reaction of RA. And if we want to, we can turn that into a negative RA, if you so please. You can say negative RA is equal to, so you can just say that negative RA is equal to all this right here. I just factored out the negatives. So here is what your negative RA is equal to. So we can say that for the rest of them, for B and C. So for our reaction rate of B, we know that B is present in both of the reactions. So we know that our reaction rate of B is going to be equal to our reaction rate of B1 plus our reaction rate of B2, which in this case is going to be equal to, our B1 is equal to the opposite of R1 we have right here. Right? So if our R1 is equal to the opposite of B1, our B1 is equal to the opposite of our A1, then it's just going to be this term right here, but without the negative. So it's going to be the exact same thing. And then for our B2 term, we're going to look over here. Again, we were given our reaction rate in terms of RC. So if we're looking at just these two comparison, we know that RB2 is just equal to negative twice RC2. So it's going to be this one right here, this term, but with a 2 in front of it and with a positive sign. Or no, I'm sorry, it's going to be a negative sign. And I actually made a mistake here. So no, I'm actually fine. Yeah, so what that one's going to be is the exact same. It's actually going to be the exact same as this one, but just with a 2 in front of it, because we know that it's a minus. It's the opposite compared to A, and it's the opposite compared to B. So it's going to be the exact same, but with a 2 in front of it. Okay, so there we go. And if we want to make it in terms of a negative RB, which you're more than welcome to, it would just be, this would just be what your negative RB would be equal to right here. Again, I didn't include the 2 before, but don't forget to include the 2. And the next one is going to be now finally for our RC. You know that our RC is only equal to whatever our rate of reaction is for RC2, which is just equal to, it's already given, right? So it's just given to you in terms of RC2 already. So let's just plug that in. Great. So that is then, here's our RC2. And you could of course leave it in terms of negative C. It's negative RC. If you want to do that, it would just be negative C2 CB squared CA. So it's really good to take a check here. So let's take a look and see, just without this whole negative factoring in, let's look at our reaction rate of A. Let's look at this line right here. And if we're looking at this line, we know that, and comparing it to the reactions up above right here, we know that A is being consumed in all of these reactions, in both of these reactions. So we should be getting a negative in both, which we do. We have a negative and we have a negative. So it checks out. Then if we're doing the same case for B, we know that B is being formed in reaction 1, but it's being consumed in reaction 2. So the first one should be a positive and the first term should be negative, which we have here. We have a positive right here and we have a negative right here. So it checks out. Then finally, for reaction C, we only have one reaction rate and we have it being generated in the second reaction. So it should be a positive rate of reaction, which we have here. We have that it is a positive rate of reaction. So we are generating C. Okay, so now we are just about done here, right? So if you wanted to, we can plug in for these reaction rates into here. So I'll just do that really quickly. Okay, so what I did here was I just simply plugged in for the rate of reactions into the, I plugged in for these given the R's that we just solved. However, I didn't do negative R because you can see right here that there's no negative R in the equations. So I just plugged in for these values right here. The negatives are already worked in and let you determine whether or not it's going to be a minus or a positive on whether or not it's being generated or consumed in the reaction. So it already takes into account if you're just incorporating the negatives beforehand. So we have here our differential equations, right? We just have dFA, dV equals all this other stuff, but there's a couple of issues here. The issue is primarily that we have concentration terms. We have CB, CA instead of DF or F terms. So since we want our flow rate in terms of, we want our concentration then in terms of flow rate, essentially is what we have to do. So if you go to lecture 6 again, I think it still starts around slide 12. You'll see that there is a formula given that says that the concentration of whatever species you're looking at is equal to the concentration total initial times your flow rate of whatever species you're looking at over the total flow rate times temperature initial over temperature. And then there's also pressure terms, but there's a little p, but we're not going to be worrying about that this one because we're not saying that there's any losses. So what we have to do is we have to plug this equation in for each one of the concentration terms that we have inside. So I'll do that for the first one, and then I will be skipping the rest, or at least just cutting to the answer. So for this one, it'll be negative Ka1 times, so our Ca is going to be squared, so I'm going to be this whole term then over here on the right is going to be squared. So we're going to have Ct initial squared times our flow rate of A over our flow rate total, and that's squared, times our temperature initial over our temperature within the reactor at whatever volume we're at, squared. Then it's going to be minus, I'm going to bring this one over Kca out in the front, and then it's Cp, so that's going to be Ct initial, not squared because there's no squared, and then it's Fb over Ft times T naught over T, and that closes the parentheses for that first one, and then minus Kc2 times, so since we have essentially a cube here, I'm going to bring a couple of cubes out, but then each one individually, the flow terms are going to be a square and a single power. So it'll be Ct naught cubed times Fb squared over, Fb over T squared, and then Fa over Ft not squared, and then we're going to have T naught over T, and that will be cubed. And that's it for that. So all we're going to do here for the next two is we're just going to plug in for that. We're given the other, given what we have for all these other reaction rates. So I'm going to do that right now. Okay, so you can see right here, all I did was I plugged in for the concentrations, and a lot of them look the same. Be sure that you don't drop your 2 here, because that was all just determined from the stoichiometry initially. So if we were doing isothermal operation, if temperature wasn't changing, and we didn't have heat removal, we'd be good. However, there's a couple of issues here, and the issue primarily is that this K term in every single reaction, or in every single term, is dependent on temperature. So each of these Ks is dependent on temperature, which is changing throughout the length of the reactor. Also, this T term is changing throughout the length of the reactor. T is a function of volume, because we're going to be having coolant. So we have to then incorporate different separate equations to figure out what these are, because they're going to be changing, they're not constant, and they're not changing as a function of volume, at least K isn't. So we're going to have to then figure out what those are, and that's going to be using the Arrhenius equation for the Ks, and then the energy balance for the Ts. So for the Ks, I guess we can write determining Ks as a function of T. So we know the general Arrhenius equation, right? So I'm just going to cut straight to that, and we know from our Ks up here, in the problem statement, we are given our Ks in different values. So right here, it's giving us our Ks and our activation energies at different temperatures and the different activation energies. Notice that this one is different. We'll get to that in a little bit. That is the equilibrium constant. So it's solved a little bit differently. So let's do that. Let's solve then for our K1. K1A as a function of temperature is then equal to K1A1, which was given, and this is just at temperature of 305 Kelvin, times EXP, exponential, of our activation energy 1, which is given, over our R, times 1 over temperature at 305, minus 1 over our T, which is changing. Okay. And then we have our K2A, which is changing as a function of temperature, is equal to our K2A2. I'm sorry, this is actually a C. K2C, K2C1, so this is just the initial that was given, and this was given at a temperature of 310, times our exponential of our activation energy 2 over our R, times 1 over T, 310, minus 1 over T. Okay, the next one is for the equilibrium constant. Now, if you look at lecture 11, slide 51, you know that it tells you that the equilibrium constants as a function of time are equal to whatever equilibrium constant at some temperature given, so we can call it T1, times, again, the exponential. However, it is the exponential of not your E, it is your heat of reaction over your R. And then it's the same as before, so it's 1 over T2 minus 1 over T. So we need to look at it's not our activation energy, it is our heat of delta H for the reaction. So our Kca at any function of T is equal to our Kca1, which is evaluated at a temperature given of 315, times the exponential of the heat of reaction. Now this is reaction 1, because that's the only one that has the equilibrium constant, over R, times our 1 over T, 315, over 1 over T. So that gives us our Ks as a function of T. So now what we've done is we were able to say, okay, now our reaction rate constants are being tracked as a function of T down the length of the reactor. But finally, we do not have how our temperature itself is changing along the length of the reactor. So for that, we need to do our energy balance. Okay, and if you look at lecture 12, slides 4, and I think there's also at slides 47, it gives you this equation right here. It gives you that the change in temperature along the length of the reactor as a function of volume is equal to your heat generated minus your heat removed over the summation of your flow rates of each individual species times the specific heat capacities of each individual species. Now let's break that down a little bit further. So we could say that our QG that's being generated, that is due to our delta heat of the reaction, and then our QR is equal to whatever is being removed. So that would be our heat jacket. So that's the UA term, right? So let's plug those in right here. And we'll say that our change in temperature as a function of volume along the length of the reactor is then equal to our negative delta H of the reaction times our negative reaction rate. Times our negative reaction rate minus UA times T minus T ambient, all that over summation of Fi CPI. A couple things here. This is our reaction term right here. That's the heat being generated. However, we have two reactions, so we're going to have to do a summation of both reactions. So let's do that. We then know that our dt dV then is equal to our negative heat of reaction, the first reaction, times our negative R formation. Here's where we have to figure out which R do we do, and that is again dependent on how you're given the terms of the reaction here. So for the first reaction, we want to be given our RA, and it's our RA1 because we're just doing the heat of reaction 1, so we just want the RA1. For here, it's our RB2. We're not including the entire RA or the entire RB because these are heat of reactions for just one specific reaction, not the whole net reactions taking place. So again, reaction rate 1 is with respect to A, and reaction rate 2 is with respect to B. So that is going to be reaction rate A1, and we're going to add our negative delta H reaction of 2. And we said this with respect to B, so it's negative RB2 minus our UA times our T minus TA. And then we have this sum term. Okay, so now we already solved for the RA1 and for the RB2 from stoichiometry above, so we can just plug those in. And if you want to, I'm going to plug in the, you can plug these in if you want to. I don't think I'm going to do that. It's a negative delta H though, so just know that for the first one, the delta H is given already as negative 20,000, so when you plug it in, it's going to end up being a positive. So let's, I guess I can plug that in. So our, this would be negative times negative 20,000, because we're just going into joules instead of kilojoules, times our negative RA1 is going to be K1A times our CA squared minus 1 over Kc times Cp plus our negative, so I guess I'll just leave this a negative, minus our 30,000 times our negative reaction rate B, which is going to end up being equal to, that's equal to negative 2 reaction rate C. So we said that reaction rate of B equal to negative twice the reaction rate of C, but we want negative B, so that ends up being positive. So it's just twice the reaction rate of C, which is given in the problem statement. So y'all can plug that in. I'm just going to say that it ends up being just twice RC. And then you have this minus UA term times T minus TA, all that over the summation of Fi CPI. Okay, that's pretty much it. So this is our energy balance for what is happening inside the length of the reactor. And then just, I guess, to let you all know, this summation of Fi term is just going to be Fa times CPA plus Fb times CPB plus Fc times CPC. That's all that is. So we are almost done, except for one thing. Our temperature A, that is our temperature of our coolant. That is like our ambient temperature. It's what is the temperature inside the cooling jacket. That's also going to change throughout the length of the reactor. So since this is changing throughout the length of the reactor, we have to create a separate differential equation for that as well. Luckily, there is already an equation that helps provide that. So if you look at lecture 12, slide 7, you have that beginning at slide 7. There are different reactions given for different directions of flow. So for cocurrent, you have that your change in your ambient temperature as a function of volume is equal to UA times T minus TA over your flow rate of your fluid times your CP of your coolant. Then for countercurrent, it's just a negative in front of it. It's just the opposite. dV equals UA. So this is actually going to be TA minus T over m dot Cp cool. Okay, so that's countercurrent. That's co-current. This is countercurrent. So what would co-current look like? Co-current is if you have flowing this way, then your heat exchanger is flowing in the same direction. For countercurrent, if you have your species flowing this way along the reactor, and the coolant is flowing in the opposite direction. Then one last thing, because the problem said, what happens if you have a constant TA? Well, all that happens is in this equation, your TA is not changing. So what's happening is if your TA is constant, then that means that it's not changing. Then that means your derivative, how your TA changes as a function of volume, is equal to 0. It's just simply that, because if you have a constant TA, then the derivative of a constant is just equal to 0. So that's all you really have there. So that's pretty much it. So let's go through now and see what would change under various conditions. So the first thing it was asking for was adiabatic conditions. So under adiabatic conditions, everything's going to stay the same up to this point. We have nothing really changing. But the one thing that is going to change is our heat of removal is no longer there. So under adiabatic conditions, this goes away. You're still generating heat. However, you're just QR goes away, and you don't have to worry about any of these bottom ones right here, because there is no TA. There's no coolant being provided to the system, so you just don't have to worry about that. So those go away. Then it's saying for what happens under constant TA. Well, I kind of told you that you would use this differential when there's a constant TA. What happens if it's countercurrent? You use this. If it's co-current, you use that. So that's pretty much it. What you need to do at this point is, if you haven't realized already, is you have to use a solver. Whether it's MATLAB, Polymath, what have you, you have to go in and plug all of these equations in, all of these constants in, and just have it solved, because there's just no way you can do it manually to solve all these equations simultaneously. I think that's it. That should do it. That should wrap it up. If I made a mistake, please reach out to me sooner rather than later. Yeah, and then so as far as for all these questions, you can just do those questions from generating the graph. I'm not going to do the code. I'll let you all have the fun. But the main part with this chemical engineering, with this class, is just getting all these equations. Once you get all these equations, you can then just have a robot do the coding and plug the coding in, and then do the graphing, essentially. I'm pretty sure that's everything. Yeah, that's going to be all. Hope you all enjoyed this.